Okay, so in today's lesson, we're going to be looking at the parent sine graph that we discovered yesterday, and we are going to compare and contrast it to another type of trig function called a cosine graph. Then we'll also look at the effect of each parameter on the child cosine function, similar to what we did yesterday with the child sine function. And then eventually, we're going to be modeling circular motion with both a sine and cosine child function. So if you recall from yesterday, here's the parent sine graph shown below. So you should remember that for a parent sine function, the 5 key points are 0, 0, 90, 1, 180, 0, 270, -1, and 360, 0. And we talked about that the function is just f of theta in this case, since our angle measure, our horizontal axis is angle measure in degrees, and it ended up just being sine of theta. Our A value was 1, our B value was 1, and our C and D values were 0. And we'll get more into that in a little bit. So now another type of trig function is shown below here, and that's called the parent cosine graph. It's very similar to the parent sine graph, but there are some key differences to look at. So the equation for cosine graph is just going to be f of theta equals cosine of theta, where theta is an angle measure in degrees. So similarly to yesterday, theta is going to represent angle measure in degrees, just like it did before. So our x-axis is still angle measure in degrees, but instead of taking the sine of theta for a cosine graph, we're taking the cosine of theta. So let's identify our 5 key points for cosine of theta. So notice our first key point happens at 0, 1. So really that would mean that at cosine of 0 degrees, if I were to go onto my graph, make sure that you're in degree mode, is 1. If I evaluate the cosine of 90 degrees to get my next key point, I would get 0. If I evaluate the cosine of, what comes next, 180, I'm going to get -1. And then if I do the cosine of 270, I will get 0 again, and then you'll notice that cosine of 360 brings me back up to my maximum at 1. So our 5 key points, 0, 1, 90, 0, 180, -1, 270, 0, and 360, 1. So let's compare and contrast the parent sine graph to the parent cosine. So you should notice that the starting point in parent sine, what we talked about yesterday, happens at 0, 0. It starts at the origin. So let's just say the y-intercept of sine is 0, 0. And that differs from in parent cosine. Notice our y-intercept is at 0, 1. So we're actually starting at the maximum value in a cosine graph. So y-intercept of cosine, it happens at 0, 1. Some similarities that you should notice, that's really the only key difference. The center line is still at the x-axis. Y equals 0 for both graphs. So that's a similarity. You should also notice that the period for one full rotation going through those 5 critical points, 1, 2, 3, 4, 5, is still 360. So it's 360 degrees for both. And finally, you should notice that the amplitude is the same in a cosine graph as well. Going from our center line up to a maximum or down to a minimum is the distance of 1 unit. So let's just put that down. So there are a lot of similarities between parent sine and parent cosine, but again, the key difference is where you start. Again, if you look at a parent sine graph, you're starting right at the origin on the center line. Remember yesterday when we were modeling, we modeled from points on the center line. For cosine, we're just going to be modeling from points on our maximum value, because that's where we're starting, so at our relative maximum. So we can model a cosine graph from 0, 1. We can model a cosine graph down at a minimum or up at our maximum. So you're always going to be modeling cosine from a min or max. And really, because they're so similar, I can actually model an equation for the parent function of cosine as a sine function. So if I were to just highlight a piece of this graph starting at the center line, I could really think of this, for example, from here to here is a sine wave, really, because we're just starting at a point on the center line. So what I have drawn there, since I really just shifted my sine function 90 to the right, and it starts by going down, if you remember from yesterday, I could really model that as f of theta is sine of theta, because again our amplitude's 1, our b value is 1, minus 90, as long as I put a negative in front of my a value. Another way that you can model the parent cosine function using sine is if we look at another point to start at. So maybe I'll start over here at 270 degrees to the right. And if I were to continue this, I can go through 5 key points as well, keeping the period at 360 degrees. I could say that f of theta is positive sine, because we're going up from that point on the center line, of theta minus 270. So really looking at a periodic function, you could model it using cosine of theta or sine of theta, depending on where you start. If you choose to start somewhere on the center line, you would be using sine. If you choose to somewhere at the relative max or relative min, you'd be using cosine. So before we try to relate this back to Kermit and try to model Kermit using a parent, it would be a child cosine function, let's just take some notes similar to what we did yesterday and how we can transform cosine so that you have it for your notes. So either on the back of one of the pages that's blank in this worksheet, or I asked you guys to get out some notebook paper, let's just title this similar. Yesterday we called it transforming sine, today we'll call it transforming cosine. So just recall from what we just talked about on the front of your worksheet, for cosine, our independent variable is our angle measure in degrees, that's theta, and then our dependent variable, y value, is just the evaluation of cosine of theta. So when we evaluate theta in cosine. So if we think about this on a circle graph, really at 0 degrees, we're at our maximum point of 1. At 90 degrees, we're at our in terms of Kermit, that would be our water level. In terms of here, we're just talking about the x-axis, we're at 0. At 180 degrees, we are down to our minimum point at negative 1. At 270 degrees, we are down at, we're back up to 0. And then back at 360, we're back up to our relative maximum at 1. So if we were to put this on a coordinate plane, theta is our independent variable for angle measure in degrees, and cosine of theta represents our y-axis. So here we have 0, 1, 90, 0, 180, negative 1, 270, 0, and 360, 1. And again, I could continue this pattern. It is periodic. It just keeps repeating every 360 degrees. So here, let me just label our key points. You should do the same as well. We could see those 5 key points of cosine. So if we think about this in terms of our parameters, our period starting from peak to peak, or valley to valley in the case of cosine, would be 360 degrees. And notice our center line is at y equals 0. So that's where we get f of theta equals cosine of theta. Our a value is really 1. Our b value ends up being 1 because, again, we just take 360 and divide it by the period. In this case, 360 divided by 360 is going to give us 1. So then if we relate this back to Kermit, remember Kermit, our independent variable was time and our dependent variable was height. So we're going to have the same 5 key points that we've been working with in class. So 0, 0, 7, 1, 14, 0, 21, negative 1, and 28, 0. So if I think about that in terms of a cosine graph, let me just label those points, and then we'll talk about how we can model this same situation that we modeled yesterday with sine using cosine. So here at 0, 0, make 7, 1 there, 14, 0, or 21, negative 1, and then back up to the water level at 28 seconds. And really, if I continued this pattern, I'd be at the maximum at 35 seconds. And yeah, let's just go a little bit farther so you guys can see a full rotation again. Maybe one more point. So a little bit more than a period here. So 0, 0, 7, comma 1, 14, comma 0, 21, comma negative 1, 28, comma 0. If I add 7 to 28, that brings me to 35, comma 1. 35 brings me down to, what would be 35 plus 7, 42, comma 0, and then 49, comma negative 1, just to get a couple more points. So now our independent variable is time, our dependent variable is height. So here, if we think of this in terms of a cosine graph, remember the parent sine function starts up at 0, 1. So really, we have our Kermit graph here, ends up being shifted 7 seconds to the right for Kermit. So instead of starting at the origin like we do in sine, if we're going to be modeling this with a cosine graph, we're really going to be shifting it 7 seconds to the right here. So our center line is still at 0. Our frequency would end up being the same because remember our b value is just 360 divided by the period. The period is still 28 seconds no matter where you choose to model from. So I believe yesterday if we got, I think it was like 12.8571 if I remember correctly. Let me just double check that. 360 divided by 28, yeah, 12.8571. So now if I want to choose to start my phase shift at this point at 7, 1, again, I don't need to put a reflection over my x-axis or in front of my a value because in the parent function, I start at a maximum point. So I can model Kermit's ride on the paddle wheel as, since there's no reflection, I just have a positive a value. Remember the a value in this case was 1, times cosine of my b value I just calculated over here is 12.8571 times t minus my phase shift, since I'm 7 to the right in this case, and then plus 0. So really this just simplifies to h of t equals cosine of 12.8571 t minus 7. Okay, so let's just generalize in terms of the parameters what we did there for your notes. So if I just, let me just quickly draw myself one more cosine graph to refer to. So we'll use degrees again, so theta and cosine of theta. So here, remember our y-intercept ends up being at 0, 1, and then we'll be at 90, 0, 180, comma negative 1, 270, 0, and 360, positive 1. And again, I can continue this pattern, repeating. So let's go through and just color code all our different parameters. So f of, and remember what we talked about yesterday, you could really have theta or t, depending on what your x-axis is labeled. So I'm going to put both there, and that's equal to. So let's just go through all our different parameters. So really we could have a plus or minus here, depending if there's a reflection or not. And then we have of cosine. Oh, sorry, I forgot our a value. Let's put that first. So I'll do a value. I believe I did it in orange yesterday. I'm just trying to stick to the same colors. Of cosine. And then we have our b value, our frequency, which again we can, I'll talk about this in a second, but we get that by doing 360 divided by the period. And then you're evaluating your independent variable. So again, it could be theta or t or x, or depending on whatever you're working with. Minus our phase shift is our c value. And then, of course, plus our vertical shift, which is our d value. Okay, so let's highlight that on the graph, and then we could just give ourselves some notes on what each piece represents. So let's start with the d value, which is our center line. So again, remember that's just what cuts the graph into in half. So our d value is just going to be equal to how far up or down the center line through 0, 0 moved. from the x-axis. And then we'll highlight one full period to identify our frequency. So again, remember, and I should put an arrow on the end here because it is continuing in both directions, our period, when you're highlighting a cosine graph, goes from peak to peak or valley to valley. So in this case, from our relative maximum to our relative maximum. If I were to continue the graph, I can go from my relative minimum to my relative minimum. So the B value ends up being your horizontal stretch or shrink. And that's also called your frequency. To get that, remember we just take 360 and we divide it by the period. And remember the period is just the time for one revolution. Next up, we'll talk about the reflection over the x-axis. So there could be a plus or minus in front of our A value here, and that's just the vertical flip over the x-axis. So if you are starting at a relative maximum, like in the parent function, there's no flip. So if you're starting, it's positive when there's no flip when you're starting at a relative max. And it's negative when there is a reflection, meaning you started the graph at a relative minimum. Our A value, our amplitude, I'm running out of room, so I'll put them under here. Our A value just represents our amplitude. And again, that's just the max minus the min divided by 2. Or more specifically from the center line, it's the horizontal distance from the center line up to the relative max or min. For the parent function, again, I should have labeled this for the B value. Again, it's just the 360 divided by the period, which in this case ends up being 1. And our center line, which I identified, I just didn't do good modeling by labeling it, happens at y equals 0. So then finally, our phase shift, our C value, in this case, since we're just starting at the y-intercept, like in the parent function, our C value would be 0. So all C represents is how far left or right 0, 1 moved. So in this case, since we're at 0, 1, we didn't move at all, which makes our C value equal to 0. So this is going to probably help you when we start modeling in terms of cosine, and then we're going to try some practice where we're modeling both in sine and cosine. So let's actually do that right now. If you go back to your worksheet, so we've already talked about comparing, contrasting parent cosine to parent sine. Let's see if we can now, if we look on the next page, refer to the graph of Kermit's ride below and see if we can write as many equations as possible using either sine or cosine. So what I'm going to actually do is, we kind of already talked about this a little bit, but we already know that our center line is at 0, our amplitude is 1, and we already talked about that our B value, I'll just put it as a note over here, is 12.8571. Again, we just calculated that by doing 360 divided by 28. So that's going to be the same. The D value, the A value, and the B value are all the same whether you're working with sine or cosine. The only difference is where we start. So if I started right here, that's a point on the center line, we're going to be using a sine function. If I started up here at this point, that's a point on the relative maximum, we're going to be using cosine. If I start on the center line at point 3 here, that would be using sine. Down here at point 4 would be using cosine. Back on the center line at point 5 would be using sine. Up at this maximum at point 6 would be using cosine. And finally back to this last point that's shown here, I'd be using sine since it's on the center line. So let's just go through and see if we can write as many equations. In this case, we can really write 7 different equations looking at all these different phase shifts. So in the first example, since we're starting at 0, 0, that is no different than in the parent function for sine. So in this case, our A value, remember, is 1. Our B value we have over here. Our D value is just 0. And in this case, since we're starting at 0, 0, our c value would be equal to 0. So our first equation, again, I'm using sine since I'm starting at a point on the center line, is going to be sine of 12.8571 times t, because I'm not shifting it all left to right and I'm not adding anything to move it up or down. If I were to start up at point 2, I'm going to be using a cosine graph. And I don't need a reflection over the x-axis because I'm starting at the relative maximum, which is the same in the parent cosine function. So that would just be cosine of 12.8571 comma t minus 7, because we're shifting 7 to the right. That one's the one that we did on our notes before as well. At point 3, I'm going to shift back to a sine function, but I need to put a negative in front of my sine because I'm starting at a point going down. So it's going to be negative sine of 12.8571, and in this case I'm shifting 14 units to the right, so it'll be t minus 14. At point 4, that's going to be a cosine graph because that's at a relative minimum. So because I'm starting at a relative minimum and in the parent function I start at a relative maximum, I need to make sure that I put a negative in front of my cosine to reflect it over the x-axis. And at point 4, that is actually shifted 21 units, or 21 seconds to the right. So it'll be t minus 21. And then a couple more at point 5, that's sine with no reflection. So that would be h of t equals sine 12.8571, t minus shifted 28 seconds to the right. Point 6 is back up at our maximum, so that can be modeled using a cosine function with no reflection. H of t equals cosine of 12.8571 times t minus, in that case I'll be 35 units to the right. And then finally our last point that's shown on the graph is at the center line, so I'm going to be using sine. But if I continued this graph, I'd be going down after that point, so I do need a reflection over the x-axis. And since that point starts at the point 42, it's going to be shifted 42 units to the right. So really, I have an infinitely many amount of equations that I could write. I really can extend this and look at Kermit on the wheel after 42 seconds. If I was thinking about practical domain and range, eventually Kermit's going to be, either jump off the wheel or eat the bug or whatever. He's not going to be on there forever, but if there was no meaning behind this problem, there's an infinitely many amount of equations that you could write modeling with sine and cosine. So really, I'm just going to put a little note. It says, how many functions can you write? Infinitely many. Really, this graph, you get a new function every 7 seconds, because you go from the center line to a max to the center line to a min every 7 seconds. Okay, so that's what we're just going to be practicing for the rest of class. I'm going to do a couple examples on the next page, and then I'll let you guys work in your groups. But really, now we should be able to model with cosine or sine, depending on where we start on the graph in terms of our phase shift. So let's just go through and identify our key parameters, so our center line, our amplitude, our frequency, and then our phase shift to determine whether we're going to use cosine or sine. So on the first example, notice our x-axis is in terms of time. So our function is going to be f of t. Our independent variable, we're going to use t. So let's identify where our center line is to start. And if you notice, the maximum value is 3 and the minimum value is 1. So that means that our center line is at 1. And you might actually recognize these graphs from yesterday. They are the same, but now we can actually model them. Instead of just using just sine, we can actually model with cosine as well. So looking at that, we've identified our d value as 1. If we look at the vertical distance from our center line up to the maximum, or from our center line down to the minimum, going from 1 to 3 is a distance of 2 units. So our a value is going to be 2. If I were to go through and highlight one full rotation, in this case it doesn't matter if we highlight one full rotation of cosine, like I did here, or I could also model one full rotation of sine, maybe if I start somewhere on the center line. So there's 2 different ways that you could highlight one full rotation. Either way, you should recognize that the period ends up being, let's see, if I choose to go from -4 to 2, that's a distance of 6 units. Or if I go from negative 3.5 to 3.5, that's a distance of 6 units. So regardless of what you chose to highlight, if you went with sine or cosine, the period equals 6. So that's going to help us with our frequency. So remember, frequency is 360 divided by the period. So in this case, I'm going to take 360 and I'm going to divide it by 6. I will get, not 30, sorry, 60 for my frequency. So I have my D value, I have my A value, I have my B value. Now our C value, our phase shift, depends on if we want to model as a cosine graph or a sine graph. So let's start with a sine graph. So let's just pick this point that we have right here at negative 4, 0. So if I chose to start my sine graph at negative 4, 0, I've actually shifted the graph 4 units to the left. So with that in mind, for my sine graph, I'm shifting 4 units to the left, and then I'm going up from that point. So I do not need a reflection over my x-axis. So for that one, I have a positive 2 as my A value. Sine of my B value is 60 times t plus 4 to represent going 4 units to the left, comma, plus 1, since my center line's shifted up 1 unit. Okay? So that would be for my sine graph. Let me just highlight sine so that you guys can color code and know what I'm talking about there. If I wanted to model this as well using cosine, I could start at the point 3.5, or negative 3.5, comma, 3. So because now I'm shifting 3.5 units to the left, everything stays the same except my phase shift. So 2 cosine of 60, t plus 3.5. And because I've started at a maximum, it's going to be a cosine function. I could also, if I wanted to, start over or down here at positive 0.5, and I would just need to put a reflection in front of my cosine graph. The second one is very similar to number 4, where time is in seconds, so I'm going to let you go ahead and do that one on your own. Maybe I'll try doing one more on question number 6, then you guys can go back to question number 5. So the difference in question number 6, notice now our x-axis is angle measures in degrees. So that's why when I ask you to write a cosine and sine equation for the child function graph below, it's in terms of theta, because theta measures angle degree. So let's start with our center line. Our minimums at 0, our maximums at 10, so halfway between would put our center line at 5, at y equals 5. So our D value is 5. Our A value, if we think about our amplitude from the center line of 5 up to our maximum or down to our minimum, is a distance of 5 units, so A equals 5. And now if we were to highlight a sine graph and a cosine graph, let me start with cosine, would have to be from peak to peak or valley to valley. So if I start over here at, it's kind of hard to see what that is, but maybe we'll just estimate so that would be for cosine, and then for sine, if let's say maybe I look at from here going through 5 key points to here. And this actually brings up a good discussion that maybe it would be helpful for this one if you had the choice. It would probably be easier to model with sine, because we can definitely see that that looks like it's about halfway between, where with cosine it's a little bit harder to tell where that is between 40 and 50. But to help you, if we think about going through, let's see here, from 25 to 115, that is the period would be 90, so that's going to be helpful for us. So let's just write that down. What color did I use? And again, how I got that, looking at the sine wave from 25 to 115. So really, if you think about taking 90 and dividing it by 4, because the period is 90, that tells you that gives you 22.5. That tells you that every 22.5 units, there's a critical point. So that would kind of help us if looking at our cosine graph, that if it happens at every 22.5 in this case degrees, there's a critical point. If I know that for sine I'm at 25, if I take 25 and add 22.5 to that, that tells me that this critical point up here that I use for cosine must be 47.5. But again, if you had the choice to use sine or cosine, it might be easier in this case to use sine because it's pretty easy to see that that is 25, 5 versus 47.5. But if you're ever wondering, again, going through 5 critical points, if you think of your circle graph, it's divided into 4 quadrants. You could just take the period, divide it by 4 to figure out at, every 22.5 degrees or units, there's a critical point. So actually this should be degrees there. Okay, so let's go ahead and actually model now. So our first example, we'll go with sine. If we're shifting at 25 to the right, we're going up from that point, so we don't need to have a reflection. Our A value we said was 5, so it would be 5 sine of, did we figure out our B value yet? We did not, so let's do that first. Since our period is 90, our B value, 360 divided by 90, ends up being 4. So that will help us when we're modeling here. It should be 5 sine of 4, parentheses, theta minus 25, since we're shifting 25 degrees to the right, and then plus 5, since our center line was shifted up 5 units. And then for cosine, since I'm starting at a maximum in this case, I do not need a reflection, so it's going to be positive 5 cosine of 4, theta minus 47.5 plus 5. But again, you could have also modeled from here for a sine graph with a reflection, modeled from here for a cosine graph with a reflection, modeled here for another sine graph with no reflection. There's an infinite amount of equations that you can use to model a periodic function. The big takeaway is for sine, you always start with a point on the center line. Cosine, you always start at a point at a relative maximum or minimum. So why don't you guys right now go back and model the same thing that we did, write one cosine and one sine equation for number 5, and then you may be able to start your homework early, which is also included in this packet. And there will be a video online for the homework in case you're struggling. Have a great break, and I will see you guys after the long week.